Hi there, it's Chem Coach Powers, and we're going to finish up Chapter 8 with a section on the activity series of metals. This is 8.3. Let's get rolling and talk about the activity series. This is one of the cooler parts of the chemistry world. There's a particular example in here about a bridge that I think is one of the coolest things in chemistry. All right, so use the activity series to predict whether a single displacement reaction will occur. You want to get out of here where if I give you reactants for a single replacement reaction, you can tell me whether or not one metal is more reactive than the other and whether or not that actual replacement will occur. If not, we'll just say, hey, no reaction. So what makes a replacement reaction happen? Well, for single replacement reactions, we look at the activity series. It's on page 266. The activity series basically tells us how active these elements are compared to each other. This has been done experimentally. This is not something you can just pull off of the periodic table, although you can see some general trends a lot of times, but there are some exceptions to it. So they've done this experimentally and seen whether or not this element will replace that other element in a chemical reaction. So a list of elements that is organized according to, get my little pen going here. Maybe, there we go. According to what? Reactivity, okay? Or activity. So that's why we call it an activity series. The higher their activity, the more reactive they are. So the list that we're going to show you are going to have a general trend. They're going to show the most active ones up here and then the least active ones down there. I will tell you that I have seen the table flipped before where the arrow is pointing down. I saw it on an AP test. They were just being tricky. So you got to watch out for that kind of stuff if you ever take AP. But for the most part, all of these are up. And so the most active will be up on top. An element in the series can replace any element below it in a single replacement reaction, but not those that are above it. All right, so can you name these as they appear? Ooh, how good are you at naming these elements? Okay, I'll just let you kind of say them in your head as we go, and I'll delay before I say mine. All right, so lithium, rubidium, potassium, barium, strontium, calcium, magnesium, aluminum. No, aluminum. It's a good story behind that, why we call it aluminum instead of aluminium like the most of the rest of the world calls it. Manganese, zinc, chromium, iron, cobalt, nickel, tin, lead, hydrogen, antimony. You got that one right. Bismuth, copper, mercury, silver, platinum, gold. Woo! All right, so the most reactive of these are at the top. So lithium is the most reactive. Least reactive of these would be gold at the bottom. Now, you'll see that another way that we've kind of arranged this is according to these different color categories here. This top little section, if you notice, they were the same kind of color separations before. The top separation is that they react with cold water and acids replacing hydrogen. So in other words, I can put these elements into cold water and they are actually going to react. And they're going to basically replace the hydrogen. And so the hydrogen is going to come out. And so it's going to give off a nice flammable gas, right? So if I put sodium in water, it releases hydrogen gas. They will also react with oxygen, forming oxides. So they would form like sodium oxide or something like that. The next category, we have all of these guys. And these are reacting with steam. Okay, but they don't react with cold water. Okay, so some things will react with steam, some things will react with cold water. And the top ones are reacting with cold water, but these bottom ones aren't as active. And so they only react with steam. They also react with acid. So they have to have more energy, basically, right, to react. That's why it has to be steam. They're still going to replace hydrogen, and they're also going to react with oxygen and form oxides. This next group is also not quite as reactive as the previous group. these guys don't react with water at all. However, they will react with acids. And when they do so, they're going to replace hydrogen. So it still releases hydrogen. They will react with oxygen and they'll form oxides. So you can form, some oxide, tin oxides, lead oxides, things like that. Now, this next one is even less reactive. These are not going to react with the acids, but they will react with oxygen forming oxides. Okay, so these guys, you can form copper oxides, mercury oxide, antimony oxide, bismuth oxide, hydrogen oxide, which is water, right? So you're going to find these things being a little bit less reactive. And then finally, our last group, which is not very reactive, these are only going to form oxides indirectly. They're not just going to react in the presence of oxygen and form an oxide. You'll have to do something to get them to do that typically. All right, so you'll notice that these are all the metals on the left. Over here on the right, you'll notice that we have some halogens. And halogens have a slightly different activity, right? All of these things are activity series of metals. But the halogens, the most reactive, are up here at the top with fluorine. The least reactive would be iodine. So this is the activity series of the halogens versus the metals. All right, so the most reactive metal is at the what? Most reactive metal is at the top. Element can displace from a compound in solution those elements listed below it. Okay. Hydrogen fits between what and what? Did you pay attention to where hydrogen was at? Okay. Hydrogen was right at the top of one of those lists. Okay, let's go back so you can see it again. Hydrogen was right at the top of one of those lists. And so it's between the lead and the antimony. Okay. And so it doesn't quite have the ability to just spontaneously react with oxygen. It's going to have some help. When you burn it, if you add some heat, okay, or electricity, you can get it to react with oxygen and form an oxide. So it fits right between the lead and the antimony, the pub and the sub. Okay, so this is what I was talking about. This is one of my favorite things in chemistry. This is something that we use as engineers to prevent bridges from corroding and rusting away. What I want you to pay attention to here is this bridge has got these different little locations where there are pieces of zinc that are able to be replaced. Okay, these are just chunks of zinc, but they're tied to the chunks of iron. You know that these bridges have rebar going through them, right? So they've got the metal that goes through them, and that helps them to be strong, but also flexible, right? So the iron is tied in or touching that zinc. Now look at zinc up here on the activity series. Okay, zinc has, in this case, they're talking about the ability that it has to conduct electricity, the mobility of metal in salt water. Basically, it's saying it can carry 1.04 volts, the way I understand this, in salt water. Whereas if you look at things like the different types of steel that might be used, I doubt that they're using stainless steel, right? But they're using the other types of metal like steel and iron, right? That kind of stuff. Those things are going to have less activity. So what happens is because they touch this zinc, then all of the electrons are going to transfer to the zinc, and the corrosion or the oxidation takes place on the zinc instead of in the iron. So see what happens here. This steel bar was basically just allowed to rust. Okay, it was kind of set out in the open, and it was in chloride doped concrete, right? Basically, it was badly corroded after a while. And this one, they were changing the process just a little bit. And so what they did is they took an anode, and after they cast this, they put the anode on it like 3 weeks after. And you see that the anode, that zinc anode or whatever anode it was in this particular case, was actually able to take away some of that corrosion. But here on this last one, when they took that anode and they put it on immediately, right? And so they attached the zinc right after. You'll notice that 9 months after evaluation, or 9 months when they did the evaluation, there's no corrosion on there. Isn't that cool? All the corrosion, though, would have taken place on the zinc. And so they have to go and they have to replace that little zinc piece, because this little zinc piece is going to get all like chewed up and nasty after a while, and they're going to have to replace that. So that way it can continue to accept these, electrons and prevent corrosion from what's happening inside the bridge. So it prevents corrosion from happening inside the bridge on the little pieces of metal they're going through the bridge. And it's all because of a single replacement reaction. That single replacement reaction is taking place where the oxygen is able to interact with the zinc instead of with the iron, because it wants to go to the thing that, in this case, the zinc, which was going to more readily give its electrons up. Okay, isn't that awesome? That's so cool. All right, so we need to now be able to do things like say, hey, will this reaction occur? Can we state whether or not this reaction occurs based upon the activity series, right? And so you want to make sure that you get your activity series ready to go. Remember, that's on page 266 of your book. If you're taking a test, we would give you this activity series. We wouldn't expect you to memorize it. Oh my goodness, I'm such a liar. I'm just looking on page 266 and it's not there. Let's try again. Wow, why would I lie to you guys? I must be evil. 272. Oh my goodness. All right, so page 272 of your book, you're like, Bowers, you're such a liar. All right, and so now we got to look up those two elements, right? So we want to find on that activity series, we want to find magnesium and we want to find zinc. Now, if zinc is above magnesium, this reaction is going to take place. But if zinc is below magnesium, it won't. So we look and we find magnesium and we see that zinc is below. Oh my goodness, if zinc is below, this reaction doesn't take place. Magnesium is more attracted to chlorine than zinc would be. And so we have to say that this is not going to happen. All right, so now you can do this with the next three. So we'll give you a little chance to pause and practice. And you're back. Let's see what we've got. When we looked at calcium and lithium, we see the lithium is right at the top. Oops. So yes, this one is going to take place. Okay. We see that, yes, this will take place. And so we'll end up, no. Calcium is trying to replace lithium, and lithium is at the top. So we're going to be like, no, this does not take place. Sorry, I just flipped those in my head. All right, now aluminum and hydrogens. Look at that one. Oh my goodness, peoples. What is going on in my brain sometimes? Okay, aluminum and hydrogen. Aluminum's way above hydrogen. All right, so will aluminum replace hydrogen? Yes, indeed, it sure will. So we'll end up with the aluminum oxide, and then hydrogen gas is going to be leaving as one of the other products. Lead and zinc. Will lead replace zinc? Zinc is already attracted, and lead is below zinc. So because lead is below zinc, this will not happen, okay? Now, we can oftentimes put NR when we want to indicate no reaction is taking place, all right? All right, so yeah, we're going to skip through that. You're welcome to practice that, but that's kind of combining together all of 8.2 and 8.3. So let's just go ahead and finish off here. 8.3 objective review. Use the activity series to predict whether a single displacement reaction will occur. Yeah, I can do that now. Given reactants for a single replacement reaction, I can use the activity series to determine which metal is more reactive. Yep, all I have to do is look at my series and see the one that's on top will replace the one that's below if they're in combination with something, right? So if I have the one that's above is free, it's going to replace the one that's combined. Okay. If the one on top is already combined, then the one below won't replace that. All right, you've done it. You're amazing. I hope you had a good time learning about this. The bridge thing is really awesome, isn't it? Oh my goodness, yes. I hope you enjoyed learning about that, because I enjoyed sharing it with you. I hope you have a great day. God bless you, and be kind to one another.